Good morning, everyone. My name is John Vola, and today I'll be presenting to you thin film preparation of silicon nanocrystals using embedded in silicon oxide by soil gel method or soil gel method. Yeah. So this class is actually nanoscale technology class, chemistry 403, and then it was supervised by Dr. Said, and I'm also a mathematics major. So, a little bit about the research background. When we talk about nanotechnology and we talk about what's nanotechnology? So nanotechnology in this case should be the study and applications of very small things. That's the basic way to describe what nanotechnology is. And in this case, nanotechnology has been applied in so many different ways and lives. And one of them is healthcare in drug delivery. So when you talk about cancer patients, people now are going into nanotechnology to deliver drugs to the affected parts of the cells. And then you talk about drinking water. People are using this to actually purify the water. And then you talk about energy. People are using solar energy and hydrogen energy, which is a source which is a result of nanotechnology. And also environment. It's good for the environment, which means it has lower consumption of materials and less damage to the environment. So with this, where we have the scramble for material, we will be able to reduce that using nanotechnology. And then what I was looking at was how to prepare thin film. So you would ask, what is thin film in this case? Actually, anything that's a thin level or atomic level structure of material on a substrate. And what kind of materials did I use in this case? I used nanocrystal silicon embedded in silicon oxide. So why did I choose to do nanocrystal silicon embedded on silicon oxide thin film? One of the greatest things actually that you can find by using nanocrystals is that it's applied in so many devices that we use on a daily basis. So you talk about our computers, our phones, you have these devices as a result of nanocrystal silicons in them. And one of them, it's because it has good light absorption and emission, which leads us to the next point. It's used in solar cells because it has what? The good quality of light absorption. And then it's used in LEDs, and then it's used also in laser diodes and photodiodes. So these are just some of the pictures showing what an LED is and what some of the electronic devices would be. So you might find something like this in your phones or in your computers or any electronic device that you may have. And why did I choose to use soil gel method? One of the reasons why was because it's cost effective. It's cheaper than any other method out there. And also it's easy to fabricate or make nanocrystal silicon in a dielectric matrix, which means this may include oxides. In this case I use the oxide. It may include nitrides and carbides. And then also it has a good uniformity. It forms a good uniformity when you make your thin film. And then also you can make thin film or thick film depending on what you are trying to get from the silicon nanocrystals. So, in my experiment procedure, this is what I did. From the beginning, I started by grinding the monocrystals of the silicon, and then from there I filtered the nanocrystals. After filtering, I made the TOS solution by adding the tetraethyl orthosilicate and ethanol absolute together. And after that, I had to make the CTAB solution, so which was a combination of hydrochloric acid and cetyltrimethyl ammonium bromide. So again, to get the suspension uniformity, a nanoscale silicon powder of 0.5 grams was mixed with TOS solution of 5 milliliters under ultrasonic for 30 minutes. And then we cleaned the wafer and curl substrates by RCA process, and later on we edged. In this case, it so happened that at the moment when we made this, spring break came by, so that was unexpected. And instead of edging the soldier by 1 day, we ended up edging it for 14 days. So which was unexpected, but we managed to do that. And then after that, we made the source suspension deposition by spinning the oxide, which was the TOS solution by itself. So we made that, and we spin coated it on the substrate, silicon substrate, and then later on we bead-doped silicon nanocrystallites embedded in oxide dielectric phase, where we were also expected to be obtained. So in simple terms, this might summarize what I did in this experiment. So the first thing, I started by cutting the substrate. In substrate cutting measurements, I used the 5mm by 10mm substrate size, and then from there I made the TOS solution, and then from there I made the CTAB and the soldier solution. After that, we left the soldier and the TOS solution for 14 days. Like I said, when that week came in, which we didn't expect. After we made the precursor, when we came back from the spring break, we made the soldier precursor. And then from there, we started the fabricating of the buffer layer. And later on, we made the soldier suspension by adding silicon dioxide solution or soldier with nanocrystal powders. And then later on, we started, we mixed the two under ultrasonic for 30 minutes, and then we fabricated the thin film, nanocrystal silicon dots. And then the thin film was dried for 60 minutes. These were some of the materials that were used. We used the TOS, 98%. We used the ethanol absolute, which was 99%. And then we used hydrochloric acid. We used also dilute 5% hydrofluoric. Silicon substrates were also used, and also boron-doped p-type silicon wafer for the nano silicone powder was used. And then in the cleaning process, we also used DI water. So the deposition conditions of the nanocrystal silicon thin film, this summarizes what took place up until the end of our lab. So I used the substrate, silicon substrate, and then I cleaned using the acetone for 15 minutes, ethanol for 15 minutes, and DI water for 15 minutes. After that, so this is how it breaks down what took place. So when making the TEOS, I had 1 mole of TEOS and 1 mole of ethanol absolute, which means I had 8.33 milliliters of TEOS and 3.69 milliliters of ethanol absolute. And I went on to make the CTAB solution, which was where I added the cetyl trimethyl ammonium bromide with DI water. So this one was, the CTAB actually was 0.2 grams in quantity. And then the DI water was 200 milliliters. And then the silicon oxide sol-gel was prepared by mixing the two. So I mixed the TEOS solution with hydrochloric acid, and that quantity came to 6.01 milliliters. And when you go down here, you see that the nanocrystal powders, I used 0.1 grams of nanocrystal powders, and then added that to the sol-gel solution that I created. And later on, I spin coated it at 11,800 revolutions per minute. And the buffer layer was made, which means it varied depending on which one, or depending on the substrate that we used. So we had times from 2 seconds to 10 seconds. And then later on, we had the sol-gel and the sol-gel suspension spin coated again. So where we were trying to do the thin film deposition. And in this case, we used the silicone substrate. So this is just a glance of what we were doing in the lab. So as you can see, I was in a suit for some reason, but I was in a lab. So this shows the thin film characterization, or the tools that are used to characterize my thin film. The FTR, TIR, and then the Raman scattering spectroscopy, scanning electron spectroscopy, or SEM, and then I used the X-ray diffraction, XRD. So now we go to the experimental results. So in this case, these were the FTIR results showing the nanocrystal silicon on the silicon oxide on the film. So in this case, we'll see that here it's showing we have the wave number here, and then we have the transmittance on the other side. And what we are seeing here is that we have these films from 2 seconds to all the way up to 4 seconds. And we can see how much light was going through the film when we look at, for example, the one that we spin coated for 10 seconds, it was found that 35% of the light was passing through the film. So out of the 100% of light, 35% passed through the film. which would lead us to the next result, FTIR result, about absorbance. So in this case, you can see we are actually seeing how the thin film is being made, and also we are seeing how the composition of oxygen. So when you look at here, as you go on top, you see that from 2 seconds, the oxygen composition is lower, and then as you go to 10 seconds, the oxygen composition is increasing. So this one now, we can find the X composition of silicon oxide and also the peak position using the two previous results that we got from the FTIR. And then the Raman scattering data shows that this one shows how well this thin film was. So it's showing the crystalline silicon powders in the thin film. So as you see here, the 2 seconds one, it was amorphous, which means the distribution of thin film or the distribution of crystals wasn't that consistent. But as you go on to these other when you go to 10 seconds, for example, or 8 seconds, you see that here the peak is at its most, which means crystals was consistent in this one. Alright, so the diffraction, in this case also we are trying to see the thin film and how well the thin film is. So we see that this is here, that's the peak of 111, and then we have another peak here which is 220. So as you are having these peaks, we know that the film is crystalline. So you can see as well here the peaks are kind of sharp pointed, and then as we go on, the peaks drop. So this one shows the intensity of the nanocrystal silicon. And then this is the SEM measurement, and on this one you see that in 2 seconds the thin film was actually it had cracks, so which means it was not we did get the homogeneous distribution in this one, but at the same time compared to the 10 seconds, you can see that now here it's more homogeneous than the other one, which means what we were actually trying to do here, or in my future research that I would try to do, is to try and work on those cracks, because you see there's so many cracks in there, so we'll try to work on that and how to make a more homogeneous distribution of nanocrystals. So the summary of results, it shows that with the FTIR shows that the composition of silicon buffer layer was greater than 1, but less than 1, but greater than 3. And then the Raman scattering shows the diameter of the nanocrystal silicon dot of 8.33 nanometer, and then the XRD shows the average nanocrystal silicon grain size of 5.4 nanometer. And the SEM shows that we acquired a crack-free uniform buffer layer. In conclusion, in the end, we were able to have nanocrystals, silicon embedded in silicon oxide using the solder method. And the Raman spectrum measurement also suggested that the average size of synthesized silicon powder and nanocrystal silicon dots were present in the silicon oxide. And then the refractive index and the FTIR measurements also suggested that the optimal film preparation having good quality should be when it is spin coated at 8 seconds. And also we achieved to prepare the thin film with the nanocrystal dots embedded in silicon oxide. Before I talk about the future plans, I'd rather talk about the recommendation and what I learned from this research. I think one of the things that I would do different with this research is time. The time was so restricted and I couldn't pretty much gather all the information that I needed in the time required. So in the future research, I would also look at the time frame. Coming into the future plans, I plan to go on and investigate more on electrical and optical properties, because this is pretty much one of the most important things why I'm also doing nanocrystal silicon thin films. So coming down here, it was not a lonesome road. There were some people who made this happen, and one of them is Dr. Sherry Pender, for her support. Dr. Mishra for letting us use the characterization tools at the University of Memphis. Dr. Hamada for letting us use the chemistry lab and also the FTIR, and Mr. Tej for letting us use the SEM measurements. And also, I wouldn't be doing this presentation today without the help and supervision and guidance of Dr. Saeed. And also, one of the people who always kept me down and, made sure that I was in class on time, Denisha Watson, and she was a tremendous help. So these are the references to my research, and thank you so much. I am a mathematics major and computer science minor. Thank you.
Beautiful.